And thank you very much for inviting me to speak. And thank you to other speakers as well, because they really set up the stage nicely for what I'm going to talk next. And I'm going to try to keep Mark's sexiness and utility of models in mind. So I'll point out the word heterogeneity, which Mark said it was one way to increase the sexiness of your model and utility, and other ones were including data, colorful graphs. So let's see if I can get some points for that as well. So what questions are we thinking of when we are preparing for outbreak, either flu or pandemic influenza or some other disease? Well, usually what we want to know is where will the cases be? If it's a novel outbreak, where can we expect the first cases to arise? How will the outbreak spread? Who will get infected and where? Who is at most risk from complications? How do we minimize deaths and infections? And basically, how do we best prevent and control the outbreak of infectious diseases? In order to answer these questions, we really need to know a little bit about context and mixing that Jonathan mentioned in detail. We need to know about who is susceptible, what kind of pre-existing immunity they have. Edwin talked about that, and I will touch upon some of these questions as well. And we want to understand better morbidity and mortality patterns from previous outbreaks and see if they can inform our knowledge of current and future outbreaks. And if we're talking about spatial spread, we have to go beyond mixing between groups and think about how the individual moves and move and spread infection from one place to another. So all of these can, of course, vary with age, but they can also vary with space, which makes modeling a little bit more challenging and complicated. But I'm going to start also with the basic epidemiological model that John already mentioned, and see how we can build it up to include age structure, contacts, and spatial heterogeneity. And then I will end with some implications for policy. I won't spend too much time on implications from policy because there's going to be a whole talk on that later on. So the basic model we've seen already. We usually model, the simplest way of modeling such things is using compartmental models where we divide the population according to their epidemiological status in susceptibles, infected, and removed class. And as the epidemic progresses, the susceptibles, I don't have a pointer, but the susceptibles are getting infected. And as the infection spread, it peaks when the susceptibles are exhausted and slowly dies out. And this model is in a closed population, but it has some very important public health connotations, namely introduce the concepts of herd immunity. So we know exactly how much of the population we need to vaccinate in order to interrupt transmission. We know something about what the final size of the outbreak will be, duration, and critical elimination thresholds. This model assumes random mixing, which we said it's not very realistic, and homogeneous population. And heterogeneity is here a complicated picture. So even though R naught is less than 1 in an overall population, if you do have heterogeneities, for example, if your susceptibles are spatially aggregated in certain locations, you can still have outbreaks, even though in overall population you shouldn't expect it under a homogeneous mixing. So when we look at past mortality patterns in flu, we can see that there is great variability with age. It's something we cannot explain with a standard model. And also, Edwin already mentioned that serology patterns for flu are highly age-specific. We have this little prior immunity in the very young, a very strong signal when we are first exposed to a flu, and then this exposure declines with age because of original antigenic signaling and antigenic superiority. And then as we age for various reasons, we see increase in seropositivity in over 65-year-olds. Part of this increase will be vaccination. If you look at more recent NPFS data that was introduced in end of July in 2009, and look at data for the UK, if we focus on where are the cases, in this case, where are the excess of cases in school-age children compared to the proportion that you would expect from census, as shown in red here is more cases than you would expect based on homogeneous mixing, and shown in blue is fewer cases than you would expect. So what we see here is quite a lack of cases in London and Birmingham. And this can be due to various reasons. That can be potentially because the immunity from the first wave, but there could be some sampling issues here too. So maybe we can use other sources of data to see for these, or to correct for these biases, which brings me to evidence synthesis that Anne talked about, which I'll again touch on briefly later. This map also, of course, illustrates spatial heterogeneity, but I will talk about that again later. So how do we include age structure? Well, if we start with a simple model, in the beginning we only had just one category, so we didn't distinguish between different ages of the cases. But now we can actually, for each age, we can classify the population according to susceptible, infected, and removed or immune cases, and that will quickly increase the number of parameters we have in the system. We can qualify this in a matrix model. Again, then we need to talk about contact matrices that Jonathan mentioned. So challenge here is that the number of compartments and the number of parameters very quickly increases. And how do we estimate these parameters? It's a little bit challenging to do it directly from case report data, but maybe we can use other sources of data. So one thing that we need to know here is susceptibility. Edwin already mentioned that the link between susceptibility and antibody titers is rather complex, so I'm not going to talk about that in detail. It does depend, of course, on the amount of pre-existing immunity we have from flu in the population. But first of all, an important thing is mixing here. Who acquires infection from whom? And contact matrices are really the key here, because they are the assumption of how the model works. And Jonathan mentioned that here we have strongly assortative mixing within school-age children, but we can see that there are also the link with the parents who are then the bridge to bring the disease to the rest of the population. So population-based surveys of social contact and mixing patterns, particularly this Polymonk study, it was really, really a game changer when it comes to modeling infectious diseases. I mean, this paper has been cited more than 700 times already because it really provides crucial pieces of information on how do we inform our models, how do contacts spread, how do diseases spread between age groups. One problem of this type of data is, of course, that these surveys happen during healthy times, or rather they are considering the interaction of healthy people, but behavior changes when we are ill. So if we are looking at a contact, again, John mentioned this briefly, if we're looking at the contact patterns of asymptomatic cases versus symptomatic people, that have big consequences for our projected epidemic trajectories. So under asymptomatic case, we can expect to see most of our cases in school-age children, whereas if we correct that for what do people actually do when they are symptomatic, we see that all of a sudden the highest affected group is 22 to 45-year-olds. So this can have implications for how do we want to deal with, for control of the outbreak as well. Another important thing is the pre-existing immunity. The population immunity also shapes viral evolution, so it's going to impact on what kind of strains are we likely to see in the future. But on more short term, it really determines who is in the susceptible pool to get infected and who has enough cross-protective immunity against circulating strains or not. Again, there are some studies, notably by Jakob Allinga, who tried to estimate pre-existing immunity, or rather, he tried to estimate contacts from information on serology. But in general, it's very challenging to get information or to infer information about our pre-existing immunity based on clinical attack rates alone. They need to be adjusted for age-specific likelihoods of exposure, so that introduces all kinds of biases and is generally hard to do. Ideally, we would use serology data, but it is not always available. However, recent studies do show that there are certain patterns. Lestrel are the first coined, I think they were the ones who coined the term antigenic seniority. They looked at a cross-sectional study of, I think they covered 170 individuals, and each line here is an individuals who are sorted from their youngest age to oldest. And one striking thing here that is shown here, the color shows the titer. Your antibody response is strongest in young for the pathogen or H3 and 2 circulating strain they observed the first, and that peaks around the 7 years of age. So during the first decade, we are exposed to our first strain of flu, and that will have the highest immune response that then later declines with age. Similar pattern was observed in a different study by Adam et al., where they developed a mechanistic model that captured both past infections and this subsequent antibody responses. So it was nice way of inferring serological data with a mechanistic model and try to explain the shapes, the age patterns of pre-existing immunity. So using these different types of data can really greatly enhance our knowledge about the system and the level of applications that a model can use. Looking then to spatial heterogeneity, and again, if we consider NPFS data, in this case, we are looking at all of the cases, and this is incidence per 100,000. And one thing that is striking here is that highest incidence is in high-density areas of North England. Maybe this is what we would exactly expect, right? We do expect to see diseases to occur in densest area. There's most people there. They're highly mixed in a closer proximity. But London and Birmingham, which are both very dense, are notably absent from this map. And the question here is, are we seeing immunity from the first wave? Remember that the NPFS system was introduced at the end of July, so the epidemic was well on its way, and it has appeared in London and Birmingham first, so maybe this is a signature of actually what has already happened in the past. Other examples of spatial heterogeneity are I'm going to use as the 2009 pandemic, but this time in the United States. It's a much larger spatial area, And in that case, they observed a very nice spatial temporal spread from south to north that was mostly influenced by school openings. So as schools were getting in session, so did the pandemic flu. And again, this is looking at a second wave. So this is August onwards. So how do we incorporate spatial heterogeneity in our models? Well, there are several ways of doing that. One way that I'm going to focus mostly is the metapopulation approach and gravity models. So in this case, our populations can be thought of as consisting of patches. Either we can think of patches as cities or regions or some other spatial units. If you're more interested in modeling social groups, then patches may represent different social categories. But in this case, we're talking about space. Network models are another very broad field of research, especially used for contact tracing and original outbreak investigation, so very important in the beginning of outbreaks. Here, nodes of the network can represent individuals, and links are contacts, either direct contacts or infectious contacts. And in case if you are evaluating a vaccination strategy like Shweta did in 2006, vaccinating individuals would essentially here be removing the nodes from the network. They're no longer participating in the disease spread. And they are indicated in these open circles. Alternatively, nodes of your networks don't have to be individuals. They can be whole cities. And the way you connect this network can vary from just looking at population sizes of different cities, or in this case, the authors were also looking at how best to distribute vaccine, and they were rescaling their network according to the amount of airline traffic and passenger flows there is in between these cities. And then lastly, we can look at individual-based models, which contain the most amount of detail. In this case, this was again the avian influenza, like Shweta did as well, considering an outbreak of avian influenza. In Thailand, that modeled a population of 80+ million people. So the individual-based models are very powerful simulation studies to inform different strategies, but for obvious reasons, they are kind of difficult to handle and infer with the data. Coming back to metapopulation models, this was the example, again, of Julia's paper that looked at 2009 pandemic outbreak in the United States. They built a gravity model where populations were organized by their size and relative distances, like a kind of classic gravity model approach. And the best model included a combination of spatial spread, so slow local spatial spread, and school openings, suggesting that children really had a big role to play in the spread of pandemic flu in the States. This is a little bit different from the way seasonal flu spreads in the States, which is more driven by adult movements and their workflow movement patterns. So this model doesn't include age structure. One way forward would be to have a model both with metapopulation and age. So if we go back to our demographic model, the previous model can be thought of only one population or one location. And now the trick is to introduce more populations, each with their own contact matrices, and that are connected with other population by movement. So here, different populations can have different contact matrices. For example, these are different contact matrices for different countries based on polymorph studies. We see that there could be some cultural differences. Some people tend to stay with their parents longer than others. But basically, in addition to within patch contact network, contact matrix, now really the key is to quantify between patch coupling and movement. One thing that complicates this picture is that now different age groups can have different movement patterns. The way children move is very different from their parents. They go to school, parents go to work. So different age groups can have very different movement kernels, and different individuals will be responsible for local spread versus seeding infection far away. This makes it a little bit challenging, and there aren't that many models so far that include a metapopulation structure with more than 2 age classes for obvious reasons. One way forward in trying to get to movement and coupling patterns is again data, and this is another paper by Adam. I think actually by the number of papers we refer to by Adam, he should really be giving at least one of these talks, if not all of them. But this illustrates movement kernels of children and adults. Bottom right is the movement kernel of adults, their commuting distance to work. And one thing that is really obvious here when we look at the other 3 graphs that represent movement of children, holidays really play an important role, as do the weekends. So movement patterns change not only by age or space, they also change in time. So we also have to think about if we need, when thinking about flu modeling, do we need to incorporate kind of term time coupling and non-term time business as usual holiday coupling. So this brings us to many challenges. Currently, methods used for fitting models, which are very popular, such as iterative filtering, deal with case reports extremely well, but they're not built to include age or space structure. So one of the big challenges here, in order to really push this kind of modeling forward, is to modify current model fitting methods and our inference with data. A key other area for using these models is using different sources of data, and really beautifully explain what challenges multiple sources of data bring. You can have conflicting evidence, you can have introduction of other biases, but we really need to consider how do we kind of have a unification of different sources of data in order to inform our models. Very briefly, going back to age structure, 2 of you already mentioned Mark's paper from 2013 and really a case for pediatric vaccination. But I will remind you that he wasn't the only one who has made that case. The case was made before. It was made even earlier than 2006. I think maybe Katie will mention that briefly. But really, children are responsible for most of the flu transmission, whereas older suffer from most complications from flu. So the case that Halloran and Mangini made in 2006, well, the older age group, so the 60 plus and 65 and above, is already very highly vaccinated. The vaccination coverage in the States in that age group is more than 60%. So extending that coverage to 90% coverage would be very, very high. So if we're comparing here the current levels of deaths on the left in this bar in the age group, so this is the deaths occurring in 65 and older, you could reduce them massively even if you introduced only 20% coverage in 5 to 18-year-olds. So you can have a bigger effect in the smaller coverage in 5 to 18-year-olds than if you were to extend the coverage to 90% in the risk group. And similar case was made by Mark. So with this, I will end and take any questions. Thank you. It was since the beginning, so since the end of July, which I guess is mostly the second wave.
Because the first wave was, the peak incidence was in London and
in Birmingham, yeah. But that is not captured in the NPFS data, hence the need for other sources of data.
I guess the presentation was quite clear. I was as well referring to a previous presentation. So thank you for nice synthesis and show how you cooperate with our policy.
Yeah.
So we keep on with policy questions, how we use models for policy by looking, I mean, the question we've been talking a lot about flu now. And the question is, should we go beyond flu? Is it, are we just seeing one part of the picture? And I think Lula Opatowski is going to do now and extend